Lecture in our series on numerical methods in civil engineering, we are going to focus on iterative methods for solving linear systems. In a previous lecture, we talked about error analysis of linear systems, and we showed that scaling of the unknowns or of the coefficient matrix has no effect on the accuracy of the computed solution except by affecting the choice of pivots. By choosing a suitable scaling, we can improve the stability characteristics of the equation of the solution procedure, but affect the accuracy only indirectly. When the coefficient matrix is ill-conditioned, but it is not excessively ill-conditioned, the Gauss elimination solution can be improved by performing iterations. What do we mean improved? Basically, we can improve the accuracy of the Gauss elimination solution by performing relatively cheap iterations on the solution. Let us recall that if the matrix is extremely ill conditioned, then we may get incorrect solutions even though we have a very small residual. Otherwise, if the residual is if we reduce the residual, we improve the accuracy of the solution. So long as the coefficient matrix is moderately ill conditioned, by reducing the residual we automatically improve the accuracy of the solution. However, if the coefficient matrix is extremely ill conditioned, then we have seen earlier that even for a totally incorrect solution we can get a really small residual. In that case, if the coefficient matrix is extremely ill conditioned, it does not make any sense to try to improve the residual, because we are not guaranteed that we are improving the solution by reducing the residual. Otherwise, if the coefficient matrix is not too ill conditioned, by reducing the residual we can improve the accuracy of the solution. What do we mean by extremely ill conditioned and moderately ill conditioned? We will talk about those definitions later on in this lecture. Let us denote our residual R as B minus A x bar, where x bar is the computed solution by Gauss elimination. If x bar were equal to x, which is the exact solution, then our residual would be 0. But since it is not, we have a residual which is given by B minus A x bar. We can therefore write A x minus x bar is equal to R. Basically, we are rewriting this equation where we are replacing B by A x, the exact solution, and then we can write the residual as R is equal to A x minus x bar. Now, suppose the decomposition of A bar into L bar and U bar is known. This is sort of because we are trying to improve the accuracy of the solution which has been already computed by Gaussian elimination. So, that means that we have the LU decomposition of the coefficient matrix. The LU decomposition of the coefficient matrix by Gauss elimination is L bar U bar. So, the assumption is that L bar U bar is known. L bar U bar being the approximate means that there is an error there because of round off. We have seen the extent of the round off, but L bar and U bar is the correct decomposition of A up to the round off error. Since the error due to the decomposition is bounded, we have seen that the error due to the decomposition is bounded provided partial pivoting has been performed. It can be bounded a priori, and we have shown that that error is small. The correction del x, which is the true solution, minus x bar, the solution that we have obtained from Gaussian elimination, we can write it as L bar U bar del x is equal to R. Basically, let us go back to the previous equation. We have A x minus x bar is equal to R, x minus x bar is equal to, we have defined as del x, and A we are replacing it by its decomposition, by its LU decomposition. So, we get L bar U bar del x is equal to R. So, we can solve this system sequentially by solving two triangular systems by denoting u bar del x as an intermediate vector y. First we solve for y, L bar y is equal to r, then once we know y, we can solve for del x. The total computations in this improvement to the original solution involves n square operations due to the computation of the residual. In order to compute the residual, we have to compute b minus a x bar. A is an n by n matrix, x bar is a n by 1 vector. So, this involves n square operations. This n square operations plus we need to solve the two triangular systems L bar y equal to r and u bar del x is equal to y. Each of these solution of these triangular systems involves half times n square operations. We have seen that earlier. So, 2 times half n square, that is equal to n square. So, the operations required to improve the solution are of the order of n square, but recall what was the total expense in the Gaussian elimination? That was of the order of n cube. So, the computations, the cost of the computation, the number of operations, and hence the cost of the computations involved in improving the solution is a small fraction of the total cost obtained in getting the solution, which is of the order of n cube. Thus, the cost of iteratively improving the solution is not significant. One may argue that new round of errors are introduced during the computation of the correction from L bar u bar is del x is equal to r, right, but those errors are not significant because that is mostly back substitution type operations, and we have seen that back substitution the errors are negligible compared to the errors during the Gaussian elimination. So, those errors are not significant. So, any new round of errors involved in which occur during the computation of the correction delta x are generally much smaller than the error that can appear during the computation of the residual. So, basically this process is two step. First step is computing the residual like this and then solving this equation to find del x. The main error during this improvement can occur during this operation. And why is that? Is it because of this product? No, it is just because of this subtraction, because we are subtracting a x bar from b, and both a x bar and b are approximately of the same magnitude, right. Since they are of the same magnitude, there will be cancellation errors, and the chances of errors occurring here are significant. We have seen that in probably our second or third lecture, that when we subtract two, for instance, two scalars, in this case we are subtracting two vectors with all of whose components are approximately of the same magnitude, but in case of scalars, if we subtract two scalars which are approximately of the same magnitude, the chances of errors are very high. So, similarly, the main error during this improvement to the solution occurs during the computation of the residual r b minus a x bar. Relatively insignificant errors occur during this operation, during the actual computation of the correction. The residual computation r is equal to b minus a x bar is prone to cancellation errors, because it involves taking the difference of two vectors, each of whose components are very close. Errors can be reduced if the terms of this product a x bar are accumulated in double precision storage, even though a I k and x bar k are stored as t-digit numbers. So, we can improve the error in this computation by doing this computation. A I k and x bar k are already stored in the computer, but they are stored as single precision numbers, normal precision. They are stored with up to t digits, right. But when we compute a x bar, we are storing it as 2 t digits. So, we try to increase the accuracy of this operation by storing it as 2 t digit numbers, and this gives me a more accurate value of the residual. Since I am computing this more accurately, r is the residual is going to be more accurate, right, because B is known, right, B is known, B is a given vector, and since I am computing this product more accurately, my residual will also be more accurate. So, this is the this process can be carried over for a number of iterations. We can perform successive iterations in this manner to improve the computed solution. How do we do this? The scheme is as follows. So, we set in the first iteration we set x bar x1 is equal to the computed solution from Gaussian elimination. Then we compute for subsequent iterations, we compute xs, s goes from 2, 3 to as many iterations we want to, as Rs is equal to B minus Axs. So, for the first iteration we compute R1 is equal to B minus Ax1, just as we saw previously, and then we compute our correction del L bar U bar del Xs is equal to Rs. We update our solution, the corrected solution, Xs plus 1 is equal to Xs plus delta Xs. So, for s is equal to 1, for x2 we get x1 plus delta x1, then go back again and go through this whole thing again until we are satisfied that our solution is sufficiently accurate. How do we know that our solution is sufficiently accurate? When my residual is sufficiently small. So, in this case the magnitude of the residual gives me a measure of the accuracy of the solution. As we discussed right in the beginning, this is only going to be true when the matrix A is not extremely ill conditioned. And we note again that only the computation of the residual Rs is equal to B minus Axs, only that requires double precision storage. So, there is not too much excessive computational cost due to double precision storage, since only this operation requires double precision storage. And it is found that Xs will converge quickly to the true solution if A is not too ill conditioned. What do we mean by too ill conditioned? That is the condition number of A, which we defined a couple of classes back. The condition number of A is lesser than 0.1 divided by n by u, where n is the order of the matrix A, is number of rows and number of columns in A, and u is my machine precision. If my condition number is less than this value, then we can say that the matrix is not too ill conditioned, and by doing this iterative procedure we can improve the solution obtained by Gauss elimination. We can improve the solution. Why do we need to improve the solution? Because solution has got round off errors. So, this is how we can try to reduce the round off errors. Next, we want to talk about iterative methods in proper. The iterative scheme we talked about just previously was improving the solution from a direct method, that is Gauss elimination, iteratively. But now we are going to talk about iterative methods proper, which do not involve any matrix inversions at all. Up till now we have considered direct methods that involve a fixed number of iterations. So, we perform a fixed number of I am sorry, this should not be iterations, this is operations. Up till now we have considered direct methods that involve a fixed number of operations. Iterative methods, however, do not have a fixed number of operations. They start from an initial assumption that is successively improved until a sufficiently accurate solution is obtained. So, we start with a guess to the solution, and then we keep on iterating, and we can show that if our iterative scheme is well posed, then eventually we get a solution which is almost very close to the true solution. Why do we need iterative methods? Because recall that direct methods, if applied to the solution of sparse systems, often destroy the sparseness. We have seen, particularly when there is pivoting required, then direct methods are going to destroy the sparseness of the system. So, thus direct methods cannot take advantage of the sparseness of the system in terms of reduced storage and operations. If you have a sparse matrix, you would like to limit the number, you would like to take advantage of the sparseness of the system by reducing the number of operations, but direct methods, because of pivoting, the sparseness gets lost and we cannot take advantage of the sparseness of the system. That is why iterative methods are useful. Large sparse systems are particularly suited to iterative methods since they do not introduce any additional non-zero elements to the coefficient matrix. Why is that? Because in iterative methods the coefficient matrix, as we will see, does not change. It remains constant throughout the iterations. For all the iterations, the coefficient matrix remains the same. So, the coefficient matrix does not change. So, there is no increase in the sparseness of the coefficient matrix. So, we can take advantage of the sparse structure of the coefficient matrix. Let us consider the system Ax is equal to B, and for the time being let us suppose that all diagonal terms of the coefficient, all elements on the principal diagonal are non-zero, that is aii is not equal to 0 for all I. In that case, we can write the solution of this system as xi is equal to any, let us consider any equation in this system of n equations. In that equation we can write xi as minus sigma aij xj, j is equal to 1 to n except j is not equal to I plus bi divided by aii. Basically this is the same, this is exactly the, if we bring ayi to the left hand side, we will get aii xi, and if we bring this the rest of the terms to the right hand side, we will just get aij xj is equal to bi. So, that is my usual any row in that equation, in that system of equations, except that I have moved one of the terms xi to the left hand side and divided the right hand side by its coefficient. So, this is identical to my usuals, any equation in that system of equations corresponds to that. And one of the most straightforward and widely used iterative methods, Jacobi's method, uses the above expression to find the sequence of operations x1, x2 and so on and so forth. So, what does it do? Well, what it does is that it starts with a particular assumption, and then it keeps on improving the solution. So, it starts with an assumption for the initial values of x, x1, x2, x3 up to xn. It starts with an assumption of the initial value, which we denote with a superscript 0, right. We start with that assumption, and then for each variable x1, x2 and so on and so forth, we solve these equations. We solve these equations to obtain updated values of these quantities. So, basically compare this equation to the previous equation. All we have done is that to the left hand side we have added a subscript of k plus 1, and to the right hand side we have we have added a superscript of k plus 1, and to the right hand side we have added a superscript of k. So, all we are saying that if we know the solution from the previous iteration, which I am denoting with the superscript k, and I put them on the right hand side, then I can get the new values of the iterate from the left hand side, because I am writing this equation by isolating each, I am rewriting each equation by isolating one of the independent variables and putting it on the left hand side. So, the one on the left hand side, that is going to give me the new value of the iterate. The one on the left hand side is going to give me the new value of the iterate in terms of the old values of the iterate which appear on the right hand side. So, we start with an initial guess to the solution. We start with an initial guess to all the components of x and denote it by x0. We put it on the right hand side, and then we find out improved guesses to each of the components of x, on the left hand side and denote it by x1 and so on and so forth. So, we go on doing that over and over again. So, once we know x1, we put that on the right hand side and we compute x2, again we do the same thing for x2 and so on and so forth. So, if we how long will it take for me to converge to the accurate solution? Depends on what starting guess I choose for x0. If I choose x0 to be close to my true solution, I will converge in relatively fewer number of iterations. However, in most linear solutions for linear systems, we do not know what is a good guess, what is a good starting guess. So, a safe starting guess is to assume that x0 is equal to 0. So, we start with the assumption that all the components of my solution are 0, put that on the right hand side of this equation, find out my improved guesses for each of the variables and do this over and over again. So, in Jacobi's method, the updated solution is not used until after a compute iteration. For example, Jacobi's iteration goes as follows. For instance, we start with all the 0 values. We know x1 0, x2 0, so on and so forth, x3 0 up to xn 0. So, we compute x1 1 from this equation, right, but now we know x1 1. So, when the time comes to compute x2 1, we could have put in this here, we could have put x1 1, but we actually put the values from the previous iteration. So, we persist with the value of x1 0 rather than using x2 1 is equal to minus a21 x1 1, the value that is known, but x3 we do not know yet the updated value for iteration 1. So, we use the x3 0 value. So, we could have used this scheme, the bottom scheme, we could have used this scheme instead of this scheme, but Jacobi's iteration says that we use the same values for all the variables during the iteration. The values from the previous iteration, we use the values from the previous iteration to get the updated values of the variables for the new iteration. We do not use any of the updated values until the whole iteration is complete. On the other hand, there is something known as Gauss-Seidel's method. In the Gauss-Seidel's method, the updated variables are used as soon as they are found, right. So, once we know x1 1, we are going to use x1 1 in the equation for x2 1, right. So, if we go back to the previous slide, Gauss-Seidel says we are going to use this, while Jacobi says that we are going to use this. The advantage is that at any point of time, only one in Gauss-Seidel, at any point of time we are storing only one value of these variables x1 through xn. So, either we have x1 0 or we have x1 1. So, we can overwrite that value of x1 0 by the value x1 1 as soon as we compute it, because once we have computed x1 1, we are not going to use x1 0 anymore. In our subsequent computations, we are always going to use x1 1. So, we can overwrite x1 0 by x1 1. So, this is an advantage of Gauss-Seidel. We do not need additional storage, but in case of Jacobi, we have to carry along 2 copies, right, because unless the whole iteration is over, we cannot throw out the old values. So, we have to carry along 2 copies of each variable. So, that is the advantage of Gauss-Seidel. So, for this Gauss-Seidel iteration, the algorithm is as follows: x1 k plus 1 is equal to minus aij xj k plus 1, j is equal to 1, I minus 1, minus j is equal to I plus 1 to n. So, for this part involves, for instance, we have this is I am sorry, this is I. So, xi k plus 1, suppose we are interested in finding the value of xi k plus 1, and suppose I is equal to 5. So, and suppose my and I am interested in finding the value of the k plus 1th iteration. So, I am interested in finding x5 k plus 1, but by the time I am trying to find x5 k plus 1, I have already found x1 k plus 1, x2 k plus 1, x3 k plus 1 and x4 k plus 1, but I have no idea what is x6 k plus 1, x7 k plus 1, x8 k plus 1 up to xn k plus 1. So, for up to x4 k plus 1, I can use the updated value, the k plus 1 value, but for x6 and so forth, I have to use the old value, the k value. So, this part I use the updated values, this part the terms which are below the principal diagonal, I use the at that row below, I do not mean, I mean below the principal diagonal term of that row, we use the old values. The terms which are above the principal below the principal diagonal, we use the new values, above the principal diagonal we use the updated values. Thus, now the new algorithm is x11. For x1 we have to use the old iteration values, but for x2, for x11 we are using x11. So, for x1 we are using the updated value, but for x3 through xn we are still using the old values. So, even though the Gauss-Seidel algorithm uses improved values as soon as they are computed, this does not ensure that Gauss-Seidel's method would converge faster than Jacobi iterations. It may turn out that for a particular problem, Gauss-Seidel may actually need more iterations than Jacobi. Only advantage of Gauss-Seidel obviously is because it's computational storage, because in Gauss-Seidel we only need to carry along one copy of my independent variables, while in Jacobi I have to carry along 2 copies of my independent variables at any iteration. So, that is the major advantage. So, any iterative method, and as you can see, if it is not true that if we perform any iteration we are going to converge to the true solution eventually. That is not true. There are only certain conditions. Each iterative algorithm must satisfy certain conditions in order to converge. So, after n iterations, I know that my solution is going to approach the true solution only if my algorithm satisfies certain conditions. And what are those conditions? Those are the convergence requirements of iterative methods, and in order to obtain those convergence requirements, it is convenient to write the update algorithm in the generalized form of a stationary iterative method. So, this is a generalized form of a stationary iterative method, which says that my improved estimate to x, which I obtain at the k plus 1th iteration, is equal to some operator b operating my old estimate x k plus some constant vector c, and k goes from 0 to 2. So, in order to obtain convergence characteristics, we write these iterative methods in this general form. All of these iterative methods, Jacobi, Gauss-Seidel, they fit into this general form. We shall show how they exactly fit into it, but they all satisfy this form. And why are these methods called stationary iterative methods? Because the matrix B, which we have indicated here, does not change from iteration to iteration. That is why it is called a stationary iterative method. For convenience, we split the coefficient matrix A into a lower triangular, a diagonal, and an upper triangular matrix L, D and U. D contains the diagonal elements of my original matrix A. L is the lower triangular part of A scaled by D inverse. So, D 1 by, basically D inverse contains the diagonal terms, inverse of the diagonal terms on its principal diagonal. So, I scale the lower triangular part of L, so I scale the lower triangular part of A by D inverse to obtain L. Similarly, to obtain U, I scale the upper triangular part by D inverse, and I put the diagonal elements of both L and U to 0. So, L contains the lower triangular part of A, except for the fact that its diagonal elements are 0 and each term is scaled by the inverse of d. So, it is scaled by d inverse. Similarly for u, in that case I can write A is equal to dl plus I plus u. You can see why this is true, because L is actually d inverse of L. If L is the real lower triangular part of A, then L is actually d inverse of L. So, d inverse cancels gives me I, right. So, I have this dl is going to give me the lower triangular part of A with the principal with zeros on the diagonal. Di is going to give me the diagonal terms of A, and du is going to give me du is actually d inverse of u, where u is the upper triangular part of A. So, d inverse of u, that is just going to give me the upper triangular part of A with the zeros on the diagonal. So, we split it, if we split it like that, then we can write Jacobi's method as x k minus 1 is equal to minus L plus u x plus d inverse of b. If we go back to the statement of Jacobi's algorithm, you will see that this is true. This is Jacobi's algorithm, right. This is Jacobi's algorithm. So, this is a k xi k plus 1, this is a I j x j, right. So, it is basically L plus u a I j is L plus u times x j, except for the diagonal term, right. The diagonal term is not there, plus b I by a I. So, d inverse b, so that d inverse b comes from this b I by a I, right. A I is the diagonal term. Let me go back and look at it again. So, this d inverse b is coming from this b I by a I, and this sigma a I j x j divided by a I is nothing but d inverse times L plus u, right, because a I j x j is L plus u, a I j x j k is nothing but L plus u. So, I can write the Jacobi's equation in this form: x k plus 1 is equal to minus L plus u x k plus d inverse of b. Comparing it with our standard form for stationary iterative methods, it is clear that b is equal to minus L plus u for the Jacobi's method, right. The Gauss-Seidel method can be written as x k plus 1 is equal to minus L x k plus 1, all the terms which are below the principal diagonal get scaled by L, the terms above the principal diagonal get scaled by u, but these involve the values from the previous iteration, while these have already been found from the new iteration. So, that is x k plus 1, plus of course, there is the term d inverse of b. So, again if we go back and look at our expression for Gauss-Seidel, we will see that this is how it looks like. This is L x j k plus 1 minus u x j k plus b, and everything I am dividing by a I. So, there is a d inverse here, but this is already built into the definition of L. So, that does not show up, right. So, that does not show up. So, minus L x k plus 1 minus u x k plus d inverse k. Therefore, b for Gauss-Seidel's method is minus I plus L inverse u. Why is that? X k, what is the general form of a stationary iterative method? It is x k plus 1 equal to b x k plus c. So, we bring this all the terms involving x k plus 1 on the left hand side. So, we get L I plus L, we take the inverse of that, I plus L inverse, we get u. So, that x k plus 1 is equal to this times x k plus this. So, b for Gauss-Seidel's method is of this form. Now, let us assume that our matrix B, which is this matrix for Jacobi and which is this matrix for Gauss-Seidel, has eigenvalues lambda 1, lambda 2, lambda 3 to lambda n, and it has got linearly independent eigenvectors u1, u2, u3 to un corresponding to those eigenvalues. Since these eigenvectors are independent, u1, u2, un form a basis for the space of solutions X. What do we mean basis? Because since these are independent vectors, any vector of dimension n where can be written as a linear combination of these u1 through un. So, these are the basis, these form a basis for that space of solutions. Thus, the initial vector x0 minus x, which is a vector of dimension n, right, can be written as some constant alpha 1 times u1 plus alpha 2 u2 through alpha n un. So, x0 minus x, where x0 is my initial assumption, x is the true solution, my initial error I can write in terms of my as a linear combination of the eigenvectors of B. We can write xk plus 1 minus x is equal to bxk plus c minus x. Why? Because this is the form of my stationary iterative method, right, except that I have subtracted x from both sides. The stationary iterative method is xk plus 1 is equal to bxk plus c. I subtract x from both sides. Let us recall that the true solution satisfies x is equal to bx plus c, because that is my true solution. So, therefore, we can write xk by plus 1 minus x is equal to bxk minus x. So, we replace xk plus 1 by bxk, right, bxk plus c, right, and then we subtract that, right. So, bxk minus x, and this I can write as b equal to b, and xk again I can write as bxk minus 1 plus c. So, xk I am replacing by bxk minus 1 plus c minus x. So, I eventually get b square xk minus 1 minus b square x. And if I take out the b square outside, I get b square xk minus 1 x. And again, if I replace xk minus 1 by b times xk minus 2 plus c, I can do this operation again, and eventually I am going to get bk plus 1 x0 minus x. By performing this repeatedly, I am going to get, every time I perform, I reduce this k by 1, right, I reduce this k by 1, but I add a power to this b, and eventually I am going to get b to the power k plus 1 times x0 minus x. Using this equation here, so x0 minus x we know we can write like this. So, substituting this value here, we get bk plus 1 operating on alpha 1 u1 plus alpha 2 times bk plus 1 operating on x2, alpha 3 plus alpha 3 times bk plus 1 x3, and so on and so forth, right. But remember that u1, I am sorry, this shouldn't be x, this should be u, right. So, alpha 2 u2, alpha 3 u3, alpha n un. I apologize for the typo, but bk plus 1 operating on u1, what is it going to give me? B operating on u1 is going to give me the since recall u1 are the eigenvectors of B. So, B operating on u1 is going to give me the corresponding eigenvalue times u1, corresponding eigenvalue if I denote by lambda 1. So, B operating on u1 is going to give me lambda 1 u1. Similarly, bk operating on u1 is going to give me lambda 1 to the power k times u1. Similarly, bk operating on x2 is going to give me lambda 2 to the power k times u2, and so on and so forth. So, eventually we can write xk minus x is equal to bk x0 minus x is actually bk operating on this, and Bk operating on q1 is equal to lambda 1 to the power k times u1, Bk operating on u2 is lambda 2 to the power k times u2, and so on and so forth. From the above equation, it is clear that if we can ensure that each of my eigenvalues have modulus less than 1, in that case this term is going to go to 0 as k increases. So, each of these lambdas are less than 1, then as k increases, since this is k lambda 1 to the power k, lambda 2 to the power k, as k increases, then this term, the right hand side, is going to go to 0. It is going to become smaller and smaller and smaller as my k increases, right. So, we can be assured that if my lambda i's are less than 1, then xk minus x is going to go to 0 as k increases. What does this mean? That means as I increase the number of iterations, my solution is going to become closer and closer to my true solution, provided my B matrix has lambda i's which are all less than 1. Thus, the iterations will converge from an arbitrary starting approximation, right. My starting approximation can be arbitrary, can be any value, maybe very different from my true solution, maybe orders of magnitude different from my true solution. But even in that case, I am assured that I am going to get to my true solution after certain number of iterations, provided my B matrix has got a spectral radius which is less than 1. What do I mean by spectral radius? It means that my largest eigenvalue must be less than 1. If my largest eigenvalue is less than 1, all my other eigenvalues are by definition less than 1. So, in that case I am going to get convergence to the true solution. Now, we have obtained this condition under the assumption that B has got linearly independent eigenvectors. However, it can be shown that even if the eigenvectors of B are not linearly independent, this condition still holds. What is that condition? The condition is that if the largest eigenvalue of B is less than 1, then my iterative method is bound to converge to the true solution. Thus, we have a necessary and sufficient condition for a stationary iterative method xk plus 1 is equal to bxk plus c to converge, is that the spectral radius of B, which is basically the largest eigenvalue max lambda I B for I is equal to 1 through n, is less than 1. B rho B is the spectral radius of B. From x0 minus x is equal to alpha 1 u1 plus alpha 2 u2 plus alpha 3 u3 plus alpha in un, we have seen that since the u1s form a basis for this space, we can write any vector in terms of this. Similarly, xk minus x can be written as alpha 1 lambda 1 k u1 plus alpha 2 lambda 2 k. This we have just seen, right. Xk minus x can be written like that. It is clear that to reduce the amplitude of the error component in error component alpha j u j, these are my error components, right, because this is my error vector and these are my error components. So, to reduce the error amplitude of the error component alpha j u j in x0 minus x by a factor of 10 to the power minus m, we have to make k iterations where k is the smallest number such that lambda j k is lesser than or equal to 10 to the power minus m. Basically, for instance, I want to reduce this error component by a factor of 10 to the power minus m. That can only happen if lambda 2 to the power k, this term lambda 2 to the power k is lesser than or equal to 10 to the power minus m, right. So, which means that k must be greater than or equal to m minus log of lambda j, right. This is the same thing except that we have taken the log to the base 10 of both sides, right. So, in that case we get k greater than or equal to m by minus log of mod of lambda j. It is clear that if the error in all the components uj, that is the total error, is to be reduced by 10 to the power minus m, then the largest eigenvalue must satisfy this equation. This is for eigenvalue lambda j, but if this is satisfied for the largest eigenvalue, then we can be sure that the error in all the components has been reduced by a factor of 10 to the power minus m, and this factor minus log of the spectral radius minus log of rho b is defined as the asymptotic rate of convergence of the iteration algorithm. It is defined as the asymptotic rate of convergence of the iteration algorithm. So, what have we seen up to now? We have seen that if a stationary iterative method is going to converge, its largest eigenvalue must be less than 1, but a priori given a set of a linear system of equations, given that we have no idea what is the spectral radius of B, right. We have to first find out what is B. We have to find out B from this expression. If we are doing Jacobi, you can find out B from this expression. If we are doing Gauss Seidel, then we have to do a spectral decomposition. We have to find the eigenvalues of this B matrix to find out what is the largest eigenvalue. We can probably use Rayleigh's method, or we are going to talk about those methods later on. We can use some iterative methods to find out the largest eigenvalue, but that is all quite expensive, right. So, a priori beforehand we have no idea what is the largest eigenvalue of B and whether that eigenvalue is less than 1, which will make sure that my iterative method is going to converge. So, we need some other indicator of convergence which is relatively simpler to obtain than actually going ahead and doing a spectral decomposition of B. In practice, the spectral radius rho b is difficult to calculate, and therefore, the criteria rho b is less than 1 is difficult to use in order to determine convergence. So, we have an alternative criteria, hence we need a convergence criteria that is simpler to use. Let us recall that we can write xk minus x is equal to bk x0 minus x. We have seen that before. Where have we seen that? We have seen that right here, right. Xk minus x is equal to bk x0 minus x. So, hence we can write mod of xk minus s, x is lesser than or equal to mod of bk times mod of x0 minus x from the definition, right, which we have discussed in probably the second lecture. We can write this, and bk is nothing but b k minus 1 b b and so on and so forth. So, I can write this is again going to be less than mod of bk, right, because bk mod is going to be less than bk minus b mod of b times k. Why? Because I can write bk as b times bk minus 1. So, mod of b times bk minus 1 is lesser than or equal to mod of b times mod of bk minus 1. Similarly, mod of bk minus 1 I can split like that, and so this thing is going to be less than that. Thus, if mod of b in some norm is less than 1, then what do we see? We see that mod of xk minus x is lesser than or equal to mod of bk x0 minus. So, as we increase, if mod of b is less than 1, as we increase the number of iterations, this term is going to become smaller and smaller. This term is going to become smaller and smaller. Therefore, xk minus 1 is going to become smaller and smaller also, because xk minus 1 must be less than this term, and this term is becoming smaller and smaller with the number of iterations. So, xk is going to approach my true solution x. Thus, if we can show that mod of B is less than 1 in some consistent norm, this is a sufficient condition for convergence. Note, this is not a necessary and sufficient condition. The previous condition, rho B is less than 1, was a necessary and sufficient condition. What is a necessary and sufficient condition? It means that it is only going to converge if rho B is less than 1, right. It is only going to converge if rho B is less than 1, if and only if rho B is less than 1, but this is a sufficient condition for convergence, right. This is not a necessary condition. So, so long as this is less than 1, we are going to converge, but it is going to converge only if rho B is less than 1. So, that is, these are two different things. This is a sufficient condition, that is a necessary and sufficient condition. So, for Jacobi's method, we know that Bj is equal to minus L plus U. Therefore, Bij I can write as minus Aij by Ai, depending on the definition of L and U. I can write Bij is equal to minus Aij by Ai, because remember what we have defined L and U to be D inverse times the actual L and U from A. So, Bij is equal to this for I not equal to j, and Bii is equal to 0 because Aii, because L and U have the diagonal term 0. So, Bii must be equal to 0. Bii is equal to 0 since L and U are triangular matrices with 0 diagonal terms. Hence, if I want to take mod of B, if I take the norm of B in the infinite norm, what is this equal to? This is equal to sigma Aij, sigma mod of Aij, Ai, I sum it over all the columns for each row and then take the maximum over all the rows. That is my definition of my infinite norm. So, I have mod of B infinity is given by that. But for a diagonally dominant matrix, which we also defined earlier, a diagonally dominant matrix, each diagonal term is greater than the sum of the absolute values of all the off diagonal terms. So, this is the definition of a diagonally dominant matrix. So, if my B matrix is diagonally dominant, if my coefficient matrix A is diagonally dominant, that means that this is always going to be less than 1, because Aii is always going to be less than this. So, each diagonal term in absolute value of each diagonal term is going to be greater than the sum of the absolute values of each of the off diagonal terms. So, this term is, we are guaranteed that this Bj infinity is going to be less than 1, and since Bj infinity is less than 1, what was our sufficient condition? Our sufficient condition was that mod of B must be less than 1 in some norm, right, and we have shown that in the infinite norm Bj is less than 1. So, that means that my Jacobi iteration, my Jacobi method is going to converge as I increase the number of iterations. So, next class we are going to look at the convergence of Gauss-Seidel, which is slightly more complicated, and then we are going to move on to a slightly modified version of Gauss-Seidel, and hopefully we will round off our next class with some discussion on iterative methods for computing eigenvalues. Thank you.